Hey everyone, welcome back to The Explainer. Today, we are definitely not just doing your standard chemistry review. I want you to put on your engineering and analytical hats right now because we are initiating a formal code review. But instead of software, our data structure today is matter itself. Okay, let's dive into this. I want you to think of chemistry as the ultimate mathematical data schema. It's a system where elements act as strict data types, and molecules are the complex objects built from them. By the end of this explainer, you'll be able to perform a complete system audit on a chemical substance, analytically verifying its payload composition, just like a senior technical product manager evaluating a brand new software architecture.
All right, here is our execution plan for today's audit. We'll kick things off with system audit initialization, look at schema architecture, syntax rules, our calculation algorithm, data weight distribution, and finally, we'll verify our payload composition. Let's get right into it. Phase 1, System Audit Initialization. So our main goal today is analytically verifying a molecular payload. But to do that, we literally have to understand the core rule of the server it runs on, the universe itself. Back in the late 1700s, Antoine Lavoisier laid down what is basically the ultimate axiom for our physical system, the law of conservation of mass. In our world, that just means that data cannot be created or destroyed during a chemical execution. It can only be reallocated. The exact same inventory of atoms, our fundamental data points, exists both before and after any reaction. You never lose data, you're really just restructuring the database.
Moving on to Phase 2, Schema Architecture, Networks versus Objects. Think about it like software. You absolutely wouldn't treat a decentralized network the exact same way you'd handle a standalone application, right? Well, chemistry is the same way. On the left, we've got ionic networks. Think of basic table salt, sodium chloride. It doesn't exist as a single isolated thing. It's this continuous repeating 3D grid, a true network topology. Because there's no defined endpoint to a salt crystal, we calculate its formula mass based on its simplest repeating ratio. But then look at the right. We have covalent compounds like water or aspirin. These use molecular mass because they act totally differently.
And that big difference really boils down to one concept: discrete units. Covalent compounds are individually distinct, separate entities. For the software engineering students tuning in, you can think of a covalent molecule exactly like an independent object class. It is completely encapsulated. It has a strict boundary, a precise number of internal variables, and it just moves through the system as one singular intact object.
All right, Phase 3, Syntax Rules, Technical Nouns.
Okay, before we get to the math, we actually need to run a quick linguistic syntax check. If we're going to articulate our findings professionally during an audit, our C1 English terminology has to be compiled perfectly. And honestly, technical English follows a really strict logic, very much like setting properties in a code class. The key here is the compound noun. In chemical analysis, we use compound nouns where the preceding words simply act as specific modifiers, basically adjectives, for the final core object. That last word is always the actual thing you're talking about, and everything before it just tunes its parameters. Let's break that syntax down. Take the term average atomic mass. The core object, our noun, is mass. Well, what kind of mass? Atomic. Which atomic mass? The average one. See how that works? The preceding adjectives precisely modify the core noun. Or how about mass percent composition? The core thing we're discussing is composition. How do we measure it? By percent. What kind of percent? Mass. Honestly, mastering this modifier to noun flow is exactly how you ensure your technical articulation is completely bug-free.
Phase 4, the file size calculation algorithm.
Now that our syntax is clean, let's actually execute this calculation algorithm on our molecular data schemas. To verify the total file size, which we'd call formula mass or molecular mass, we just run a simple 3-step loop. Step 1, identify the constituent elements. Step 2, multiply the atomic mass of each element by its subscript. You can think of the subscript as the inventory count for that specific data type. And step 3, sum the totals to get your final payload size in atomic mass units.
Let's run a live execution of this. Here we're looking at an aluminum sulfate schema. Following our algorithm, we identify 3 constituent elements: aluminum, sulfur, and oxygen. Next, we pull their average atomic masses, basically the file sizes of the individual atoms, and multiply them by our inventory count. So that's 2 aluminum, 3 sulfur, and 12 oxygen. We calculate those subtotals, sum them all up, and boom, we get a total formula mass of 342.14. Algorithm executed successfully.
Moving right along to Phase 5, data weight distribution.
So, knowing the total file size is really only half the battle. Now we need to shift our focus to internal resource allocation. Basically, how is that data weight actually distributed across the structure? Let's use a brand new target data schema for this, ascorbic acid, which you probably know as vitamin C. This is a discrete, encapsulated covalent object made of carbon, hydrogen, and oxygen. We already know how to find its total mass, but to really understand its system architecture, we have to uncover its metadata.
And in this case, that metadata is its percent composition. This is totally crucial because it shows us exactly how the full 100% of the molecule's mass is proportionally distributed among its constituent data types. The math here is incredibly straightforward. Mass of the specific part divided by the total mass times 100. For ascorbic acid, this resource allocation works out to 40.92% carbon, 4.58% hydrogen, and 54.50% oxygen. It's this exact proportionality that actually defines the chemical identity of the substance.
Finally, Phase 6, verifying payload composition. This is the part where we bring the math and the professional articulation together to report our findings for the real world. But first, a super quick note on professional reading practice. When you're reporting these metrics in an audit, precision in your speech matters just as much as precision in your math. You wouldn't just say 12.1%. No way. You articulate every single significant digit. We read this professionally as 12.01% by mass. Doing it this way ensures absolutely zero ambiguity when you're transmitting data to other engineers or analysts.
Now, you might be wondering, why does this level of rigorous analytical verification even matter? Well, consider industrial applications, like massive copper fermentation tanks. When you are using bacterial fermentation on grains to make ethanol, gases are produced as a byproduct and channeled through these complex pipes. Engineers have to constantly audit the gas payload composition to make sure the process isn't failing. By capturing a sample and determining its mass percent composition, let's say they find 27.29% carbon and 72.71% oxygen, they can actually reverse engineer the empirical formula to verify that the system is safely venting carbon dioxide, CO2. It is literally the exact same logic we just walked through, just scaled up to massive industrial proportions.
We've seen exactly how to audit fixed, static data schemas in chemistry today. But I want to leave you with one final thought to ponder. If a single chemical formula is just a rigid, unchanging class definition, how do massive, complex biological networks, like the human body, constantly reallocate these resources and handle dynamic payload updates every single second without the entire system just crashing? The math is exactly the same, but the server architecture is infinitely more complex. Think about that the next time you take a vitamin. Thanks so much for joining me on this explainer, and I'll catch you next time as we continue to decode the systems around us.